Okay, so hopefully you guys remember why pi groups are important, right? They allow us to predict the behavior of a prototype based on the behavior of a model when we might not have an analytical relationship or an analytical model at our disposal. Um, so let's assume, though, we aren't given these pi groups, that we have to find them. One way we could do this is what we call through inspection, which basically means, trial and error. And if you've done this for years, you can actually become quite good at it. For example, by the end of this section, I hope that when you see something like rho VD over rho VD and mu, these four, see, it's already so natural to me, I started to write it, the Reynolds number already. But if you see these four physical variables, then you need to make a dimensionless group out of them. You'll just be like, oh, well, I can just divide by mu, and this is the Reynolds number. Bam, done, right? And you can become quite good at this if you do it a lot. Let's assume, though, for now that you aren't quite good at this yet, and you need a systematic way to find these dimensionless pi groups. So the first thing we're going to do is we're going to write down all of the parameters involved with units. So all parameters with units. And this is just an organization step, but it's really important because where people typically make mistakes in this is at this first step. So if I'm taking off points on an exam, it's usually because you screwed up here. So let's stick with our ball falling or ball in a stream of air problem, and we will write down all of our units. So the first one is our drag force. Another variable is density. Another variable is the velocity of the fluid at infinity, so far away. Then we have diameter, and finally we have viscosity. And we're going to write down the units, but we're not going to write them down in SI units. We're going to write them down generally in terms of mass, length, and time, M, L, and T. So force is mass length per time squared. Density is mass per length cubed. Velocity is length per time. And our diameter is obviously just length. And our viscosity is a mass per length time. Great. And now we're going to count up the number of physical variables we have. 1, 2, 3, 4, 5, which gives us n is equal to 5. And step 2 is figure out the number of pi groups. And just a friendly reminder that while we're doing this, while I'm saying these things out loud, you get the most retention if you try to not just copy what I write down on the screen, but to rewrite it in your own words, rearrange it, try to extract the meaning of what I'm saying and express that meaning in a different way, right? And that is the way you'll get most retention. Remember, like we said, it's 60% more effective, which means you need to spend half as much time studying. Okay, so figure out the number of pi groups. So our equation for the number of pi groups is P is equal to n minus k. In this case, we know n is equal to 5. So we have this is equal to 5 minus, but we have to figure out k, the number of physical dimensions, right? Primary physical dimensions. So here we have mass, length, and time. So that's 3. And that gives us 2 pi groups, right? We already know what those 2 pi groups are. If you go to the previous lecture, I already gave them to you. But we're going to figure them out here. And actually, you know what, let's mix it up a little bit. We're going to find some different pi groups, which is a good lesson that there are actually tons of different pi groups you can find for any group of physical variables. So for this group of physical variables, there's a bunch of different pi groups we could find. Not all of them are useful, So we'll find a different pair than what we found previously. So we'll show you how to do that too. So we know that we need 2 pi groups. Great. Step 3, we got to choose our repeating parameters. And this means our building, what I like to call our building parameters. What does this mean? Well, repeating parameters are physical variables that appear in every pi group, or could appear in every pi group. They don't have to, but they could appear in every pi group. So we have, if we go up, let's rewrite our, we have them right here. So we have, if we look at our group of physical variables, we have force, density, velocity, diameter, and viscosity, right? And we need to pick 3 of these. So we need to pick, basically, we need to leave, we're going to build pi groups around 2 physical variables and use the remaining 5 minus 2 equals 3 physical variables as our repeating parameters. So I want to build, for this case, I'm going to build pi groups around our force and our velocity. Force and our velocity, which means that our repeating parameters are going to be density, diameter, and viscosity. So we have rules for how we pick these repeating parameters. And let's go over those rules now. These rules don't necessarily apply for this particular example, but they will in future examples, and we'll go over them a bunch, but let's write them down here. So rule number 1, your repeating parameters must include all dimensions. So repeating parameters must include all dimensions, right? So what does that mean? Our repeating parameters, which are circled in red, must have length, mass, and time represented in some way. So we have length, check. We have mass, check. We have time, check. Good, we're done. It can have multiple masses. Density also has mass, but we have to have them in at least one of them. All right, number 2, our repeating parameters must be dimensionally unique. What does that mean? Let's say we also put, instead of diameter, we also had radius here. The units on radius are length, and that means that we could not choose radius and diameter as our repeating parameters. So we wouldn't be able to choose that. We'd have to build a pi group around radius. Great. So the last rule, which is probably the most complicated, is the repeating parameters must not be powers of another repeating parameter. What does that mean? Well, we could also choose cross-sectional area of our ball, for example, as a physical variable. Now, it's not a very meaningful physical variable, which is why we did not include it in the original. We also didn't include radius because it's not very meaningful, because radius is just half of the diameter and area is just diameter squared times pi divided by 4, but I'm just using these as an example now. So if you were doing dimensional analysis on a plane, for example, you have tons of dimensions. You could use the area of the wing, the length of the plane itself, right? There's all kinds of variables, lengths that you could use where this would actually apply, and you would have them included in your system of variables. But your area is actually length squared, right? So you could not choose area and diameter as both repeating parameters, because area is diameter squared, right? It's the power. It is a power of another repeating parameter. In this case, that power is 2. if it is squared. So we couldn't choose that. All right, so we have our repeating parameters. We've chose them. We will generally give these to you, right? Choosing repeating parameters is, like I said, if you choose different repeating parameters, for example, we could have chosen force, density, and velocity as our repeating parameters, and we would have gotten different pi groups. So honestly, to make it so that everybody has the same, or is doing the same problem, we usually pick the repeating parameters so that you end up with the pi groups that we expect you to end up with, right? But it's important to know the rules for picking those. 2, step 5. This is where the rubber hits the road. We're going to write out our pi groups with exponents. Pi groups with exponents. What does that mean? Well, remember back to our Reynolds number example where we have rho v d over mu. We could rewrite this as rho to the 1 power, v to the 1 power, d to the 1 power times mu to the negative 1 power, right? So we're going to try to solve for these exponents that result in canceling out all of the units for our problem. Okay, so if we write this out, what we're going to say is that 0 is equal to F, our drag force, times rho to the A, which is our first repeating parameter, because we're going to build our first pi group around our force. That's this physical variable there. Rho to the A, d to the b, and mu to the c. And then we're going to write these out in terms of their fundamental physical dimensions. So this is actually mass length per time squared times mass per length cubed, all raised to the a power, right? Times length raised to the b power, b, times mass per length time raised to the c power. Great. And now we're going to solve for the a, b, and c that result in all of these physical dimensions canceling out. Okay? And you'll note that we have 3 variables, a, b, and c. We have 3 physical dimensions, mass, length, time. And if you have 3 variables, you need 3 equations in order to solve for them. So we're going to end up with 3 equations. The way we're going to do that is we're going to write out the powers on all of the physical dimensions as sums of each other, right? Because if we have mass, for example, if we have mass to the 1 power times mass to the negative 1 power, those cancel each other out, right? And that's because 1 plus negative 1 is equal to 0. So when we sum all of the powers of our masses, we'd expect them all to be 0 if all of the masses cancel out. So let's do that. Let's start with mass. We do mass. We have 0 is equal to, because remember all the sum of these have to equal 0. We do the first one. The first one of the mass inside of the force is going to be to the 1 power. So 1 plus mass to the a power is just a, plus no mass in our diameter, so we just have a 0 times b, plus m to the c power. M to the c power. Good. Now let's do our next one, which is mass length. Let's do length. We have length. We have 0 is equal to, and then we have a length on the top, so it's just to the 1 power, plus a length to the third, negative 3 on the bottom here. That's a negative 3. So we have a negative 3 times a for that. We have a length to the b power here, so that's plus b, plus we have a length on the bottom, which is a negative 1 times c, gives us a negative c. And then we do time. We have 0 is equal to, we have t to the negative 2 here, so that's just a negative 2, plus no time here, great, 0 times a, plus no time here for our diameter, so we have a 0 times b. And then finally we have a time on the bottom, and it's just a negative 1 times c, so negative c. Great, and we have 3 equations and 3 unknowns. You have done this, solved this type of problem since, I don't know, 8th grade, 7th grade, who knows, a long time. You can pause the video and try to solve it right now. I will tell you that the answer to this problem is pretty straightforward. We can solve for c first, and we find out that c is equal to -2. And we can plug out, oh, I wrote this wrong, m times c, that's not right. It's just c up here. So we put a -2 into here, and for this c, solve for a, and we get that a is equal to 1. And then we plug both of those into the length equation, and we find out that our length is equal to, our b is equal to 0. Great. So if we write out now our pi group, our pi 1 is equal to FD, our drag force, because remember that's just there, and we're using all of these around it to cancel its units out. Our density is going to be multiplied, is to the 1 power, so it's F times density divided by, there's no diameter, but our viscosity to the -2, so viscosity squared on the bottom. That's our pi 1. Great. Now 0 is equal to, let's do our pi 2, our second pi group. Our second pi group is going to be built around our velocity, because that's the other physical variable we didn't use for our repeating parameters. So v at infinity times, again, we just reuse the same repeating parameters. That's why they're called repeating parameters. They're repeating. Rho to the a, d to the b, mu to the c, which is equal to now length per time times, and then everything else is just repeated from what we had before. Mass per length cubed to the a times L to the b times mass per length time to the c. And now we can go through again and write out our equations. I'm going to let you pause the video and go do that yourself. A hint, again, things tend to repeat. So this column changes, but everything else stays the same because everything else is related to our repeating parameters. So go ahead, write down our new set of equations, and then restart the video. Again, this is engaged learning, right? This is you trying to synthesize stuff and do it, and then we can, rather than just rote writing it down. Okay, so let's do it. We have mass is going to be equal, 0 is equal to 0 plus a plus 0b plus c. Length, we have 0 is equal to 1 plus -3a plus b minus c. And then time, we have 0 is equal to, we have time on the bottom here, so it's going to be -1 plus, and then everything else is copied from before. So 0 times a plus 0b minus c. Great. And this is a relatively straightforward set of equations to solve again. We can do c first, and we find out c is equal to -1. And then if you remember, this was a set of variables that I said that we could easily, you should easily, by the end of this section, be able to be like, oh, that's the Reynolds number. But if you go through and solve this system of equations, you'll find out that a is equal to 1 and b is equal to 1. And what we end up with is pi 2 is equal to rho v d over mu, where v was our physical variable we were building these around, and rho, d, and mu are our repeating parameters. Great. So Buckingham pi theorem then tells us that with these two pi groups, we know that pi 1, oh, I forgot to delete this page. Let me delete this page here so that I can write it for you guys. Buckingham pi theorem tells us that pi 1 is equal to some function of pi 2, right? That's what Buckingham pi theorem tells us. It doesn't tell us what this function is, but it does tell us that. So we know that force times density divided by mu squared is equal to some function of our Reynolds number, rho v d over mu. We could also write this as some function of our Reynolds number. And just do that, and that is sufficient. So in our next video, we're going to practice this again, and we're going to ask what will happen if we choose different repeating parameters, right? if we choose to build our pi groups around different physical variables. So before, remember, we chose this and this, our force and our velocity, to build our repeating parameters around. And our next video, we're going to choose different repeating parameters. And we're going to see that we get different pi groups.